Hi, we're going to get into some mechanical and chemical weathering, in other words, breaking stuff down. But as a really quick review of the law of superposition, I just want to remind you that the farther down you go in your layers, you should have older material. So the farther up we go, the newer it is, the farther down we go, the older the layers are. And that's our relative age versus our absolute age. Remember, absolute aging is when we can use carbon 14 or uranium decay to figure out exactly within a given margin of error. Relative age is the older stuff's on the bottom, the newer stuff's on the top. A quick review. Now we're getting into weathering. So what is weathering? Weathering is the breaking down of rocks and other materials on the Earth's surface. So in other words, you can take a really big mountain range. Minnesota used to have a mountain range that rivaled the Rocky Mountains a very, very long time ago. That basically has worn down to what we have now, plus a lot of glacial material debris piled on top of it. But really, we're talking about the breaking down of um, rocks into soils. Eventually, that's where we're going to get. We're going to go through a number of actions of mechanical weathering. The one I'm going to hold out separately, however, is glaciers because, well, they're cool and they warrant a whole day. So, physical processes, mechanical weathering has nothing chemical about it. This is all physical changes. So, like if I take a wire coat hanger and I bend it into the shape of a puppy, it's still the same metal, just in a new shape. I haven't changed its chemical composition at all. So there's different ways that we can um, move things or break things down through mechanical processes, one of which is pressure release or release of pressure. And think about this, imagine a really hot day and you touch that rock and it's really hot to the touch. But the problem is, if you go a few layers in on that big rock outcrop, it's not as hot as the surface is. So you have an uneven expansion of the rock on the surface. It expands. Kind of think about your fingertips when you're in the bathtub and or you're swimming, or you're in a lake or a pool, whichever one you swim in. Um, your fingers get puckery because the outer layer of skin is absorbing water faster than the inner layers can catch up, and you get puckers on your skin. Well, the same thing can actually happen with rock. This outer layer expands as it gets hot, and the inner part doesn't expand at all because it's not as hot. And then remember, in the winter it gets cold and it contracts, so you get this. You can also get freeze thaw, which we'll talk about here in a second. But this is the release of pressure. So what happens is, with that expansion, eventually it expands and contracts because remember, at night it cools down and then the next day it gets hot again because the sun comes out, and you have this repeated expansion, contraction, and eventually it cracks or flakes off. In fact, you can see different layers of this rock right here have flaked off. You can see it better here. So that's a release of pressure. Now, a freeze thaw is kind of the same idea, but it has to do with cold. So now imagine a little crack in a rock and water gets in there and then it freezes at night. By the way, this is how a pothole forms in our winter. We're just coming out of pothole season. They're getting fixed now. And as water seeps in, remember, water is that one substance that when it freezes, it expands. Everything else contracts. So this water gets in here and it forms a little wedge and it freezes and expands just a little bit, making that crack just a little bit bigger. And with that, then the next day, maybe it warms up and a little more water drips in there, or it doesn't. Maybe it's just the same water and it hasn't evaporated because it's too cold. But let's say it melts and it slides a little farther down into that crack and then freezes again that night. And that repeated freeze thaw eventually pops that crack off, and you see this whole piece of the rock has actually cracked off with freeze thaw cycle. In fact, here's a crack and there's a crack, and there's has three different chunks of it broken off into four pieces, three different cracks. Plant growth. Oh my gosh, plants. Have you ever been on a sidewalk and riding your bike and there's this one little part of the sidewalk that's just a little bit raised up because a tree root has popped it up? Be very careful because that can really hurt you. But tree roots can find a niche and grow into a little tiny crack in a rock, and as that tree root grows, Usually the rock will eventually give and it can crack off pieces. Animal action, moles, voles, gophers, anything that digs, ants, anything that digs can churn the soil, and they can get in there, and because they've made tunnels and holes, it allows water to get in, and then you can have freeze thawing, or it can have we'll get a little bit into chemical weathering. It could allow water to get in there and leaches some of the minerals out. But animals actually break things down because they just move stuff around. And the last one, which I'm holding off to last, is abrasion. Now imagine it's a really, really windy day. And we just had this happen. My neighbors were having a tree cut down, and they were chipping it. And I was talking with my neighbor. I was socially distancing. I was appropriate. But the little fine particles from that wood chipper kept flying at us, and they kept going into our eyes. And we were both like, we finally both had to turn around because it was so bad. Now imagine you're in the desert on that really windy day, and it's not wood chip particles, it's little pieces of soil and sand, and you can get something called a sandstorm. Well, imagine that sandstorm hitting rock. That's like sandblasting, and it can sculpt rocks into just beautiful shapes. So quick review, think this through. I see a rock here and I see flakes coming off. What do you think that means? What kind of mechanical weathering is that? Is it animal action? Is it abrasion? Is it plant growth? Is it freezing and thawing? Or is it release of pressure? When you see this kind of flaking, you should start thinking of release of pressure. This is another release of pressure. This is an exfoliated rock. So do you see all the different spots on here? It's literally cracked off different layers. As this rock heats up, there's pieces of it down there, and there's pieces about to fall off. If you can look, there's some right here. But this is that same process. So what is this? You should have a pretty good idea. I'm seeing snow, and I'm seeing that same rock, and I'm seeing a big rock here split, and here's one in a bunch of different pieces. This is the freeze thawing mechanical. It's breaking a rock down into smaller parts. And the interesting thing is, the more surface area it has exposed, we can get into that when we get into chemical weathering, it can actually start breaking down faster and faster. A big boulder doesn't, it's got a lot of surface area, but if you start cracking that into small pieces, you've literally exponentially increased the surface area, and you allow for a lot more weathering to occur. So if I look at this is, I believe, Cornwall, and it's just a minute long, so bear with me. I might have to turn the volume up or down, so here we go. Maybe.
Believe it or not, the rolling countryside of Cornwall in southwest England used to look more like the Himalayas or the Alps. Mountains don't last forever. They gradually wear away at a rate of about 10 centimetres every 1,000 years. So all that's left in Cornwall today is a series of domed shapes, giving the landscape its rolling appearance. Changes in temperature from day to night and the expansion of freezing water cause rocks to wear away.
You can see that crack forming.
When water enters a crack in a rock, it expands as it freezes overnight. When the ice turns to water and freezes again, it forces the crack open a little more. As the water seeps even further, the crack widens. This freeze-thaw action is repeated. It eventually causes pieces of rock to break off. They fall down the mountainside, where they lie as pieces of jagged rock known as scree.
That slope's called a talus slope. It's a debris slope, and it's at something called the angle of repose, which is the steepest angle it can go before it slides down. So that is a talus slope. Okay, here is our wind action. These are sculpted rock, usually of like this layered here, the layered rock here. It looks like somebody's like surgically gone in and taken out. More than likely this was a sedimentary rock that had different alternating layers of harder rock with maybe some quartzite or basaltic lava flow, depending on where it is. I don't think this is basalt, but and then interspersed with maybe like a sandstone layer that's very erodible. And it's actually, as the sand blasting with the wind hits it, it erodes away the softer layers faster, and you get these beautiful shapes. Or here, you know, what you're really seeing is this, you're not getting as much, or probably the wind is high enough that it got to this point, but it didn't get all the way up here. And what happens is, as it picks up sand, it erodes away. And if you look at this one, this, you can kind of see the layer where the bulk of the sand is really hitting, and you get these things called desert mushrooms. And because it kind of looks like a mushroom shape, right? The bottom stem is being eroded away because that's kind of the layer at which the sand rises as the wind goes and it gets blasted more. And you can also get these beautiful arches where the whole center has been basically blasted out. And if you go to Arches National Park, you can see some really beautiful ones. These are some of those mushrooms in the White Desert in Egypt. Remember, all these videos, you can go into the notes that aren't worth any points, but you can watch all of this again without having to, well, watch the whole video. But if you want to go do a review, you can.
These outcrops are standing in Egypt's widest.
And you can see the sand blasting down here. It actually digs a hole out.
And turned into more sand.
Aren't they beautiful? Eventually, this can become so weakened that this will topple over and it'll be literally on the ground, and then it will start wearing away faster and faster as well. Alright, you get the idea. It's in there if you'd like to go watch it, but there's beautiful scapes.
Heavily eroded rocks have been removed in the sea sand.
So at one time, all of this was probably a sedimentary rock layer, and it's worn away in the middle. If you want to finish that, you certainly are welcome to. And here is another one, but this is a little bit longer, but it's showing you some more of that. So if you want to take a look at it, please do. Beautiful. Like, you can see holes here that have been eroded away, and more of those rocks that have been stranded in the middle as they get sculpted farther and farther down by the wind and abrasion of the sand. But again, I'm not going to show all of that, but it is there if you want. Here is our, what would this be? This would be your plant action. This is, if you look at this tree. It's crazy. It is literally straddling a ravine. I'll make that a little bigger for you. And they got baby Groot because, well, you have to have that because his roots would, you know, push stuff away too. But it is hanging on to each side of the cliff, as actually part of it has worn away. These roots were actually at one time probably in the rock, and as that rock disintegrated through water and some plant action, it's leaving this tree literally suspended, hanging in midair. And these are lichens, and this is actually lichen, and then moss would be the next. That's getting into soil succession, which is a different stays note. But you can see mosses here and lichens, and this is actually a chemical process. It excretes a slight acid, which breaks down the rock, but that is a plant action, actually bordering into the chemical, but it is plants doing it. Roots will take hold wherever they can, and they can break up the rock. Now I suppose I need to make this just a little bit smaller. So animal mechanical weathering can cause wedging between cracks. Burrowing, fragments, and den making activities can also cause rocks to be exposed. And then as the rocks are exposed, other things can get to it to start breaking it down, whether it's frost action or any of those other mechanisms that we've talked about.
Welcome to the Earth Science Research podcast series created by Columbus Middle School Earth Science.
Is a podcast. I think it's about 7 minutes long. Yep, 7 minutes, 9 seconds. And this is a review of mechanical weathering. So if you want another person's opinion and explanation, go ahead and watch it. That is perfectly okay. Now we are getting into chemical weathering. There's 3 main types we're going to really talk about. Carbonation, that is CO2 plus a little water. and you have becomes slightly acidic, and it breaks things down. And acid plus minerals, they don't like it. Remember, if you were in with either Mr. Cater or myself, we put a little acid on calcium carbonate, and that's a mineral, and it reacts with the acid and it fizzes and breaks down. Well, that is carbonation or carbonic acid reaction. Hydration, water leaching through the soil, pulling minerals out, can create erosion as it basically gets drained through. And then oxidation. This is a really technical term. I'm sure you will have seen this probably a lot in your life. You just didn't realize it was an oxidation, and that's rust. Anything that's got iron reacts with air and rusts. That is a breakdown. Copper turns that beautiful patina of green, and that's an oxidation reaction. So we are talking about that formation of soil, and we're getting into living organisms. So some plants and animals can produce really weak acids that chemically weather the rock. So in other words, now we're no longer just doing physical. We're getting into physically changing what the stuff is. Lichens work very slowly to break down granite, and this is the first indication that we're going to start getting a soil in the area, because those lichens can start to break down the rock itself with the acid, and then eventually mosses can come in, and then you get more debris and detritus, and eventually you get a soil. So oxidation is rust. This is the red rock in Australia, and here's the red rocks. And iron, our iron ore up in northern Minnesota is iron filled, so it's rust, it's red. I can tell you, when I was younger, we had a Samoyed, which, if you don't know what that is, it's a beautiful pure white sled dog with hair that's like 9-10 inches long in places. Fluff ball, beautiful dogs, really good with kids and families, but they like to run, so be careful with that. We had gone up to northern Minnesota to my uncle's cabin, which is in the Iron Range, and just as we were about to leave, she got away, because she's a runner, and her name was Nikki. And she ran for the lake, came out of the lake and rolled in the red clay. And so we not only had a wet dog with no air conditioning and the windows rolled down, because this was the 70s, we had an orange dog because the iron dyed her fur. So the red clay turned her fur orange. So white dogs, red clay, bad combo. But this is oxidation. So this is rusted rock. Literally, it's a rusted rock. All of these are rusted rocks. So a little water plus a little oxygen plus a little iron, you get rust. So when you see this kind of color, there has to be some iron in those hills. Carbonations, which is carbon dioxide plus water, gives us H2CO2. And if we look here, we've got water, carbon dioxide, and you end up with our handy dandy carbonic acid. And you can also get some hydrogen ions, and which can plus a little bicarbonate ions. Calcium carbonate plus carbonic acid gives us calcium ions and bicarbonate ions. I don't expect you to remember all this. You just need to know that basically you're having a chemical reaction that is taking pollution from our air and turning them into weak acids. That's why right now, with everything really not functioning in this lockdown, we have the air getting better. But things like Venice right now, people, the dolphins are back in Venice. They're seeing them jumping in the canals because the water isn't as polluted. Places like Greece, which have beautiful marble sculptures, are not, their faces that used to have definition in the last basically 80 years have lost most of their definition through this kind of action, through chemical weathering. And it's because we put pollutants in the air, and it reacts with things in the air and carbon dioxide and other chemicals, and it turns them into a weak acid, causing acid rain, which over time, that acid, just like when we placed it on the calcium carbonate, which is marble, which is old seashells, kind of like, think of it that way, starts to break down and lose definition. So we are eroding away our sculptures. Acid rain not only can wear away marble, but as it hits the pine forests, which are acidic themselves, it actually kills the pine needles, and it will deforest entire forests. All the needles will fall off, And as it goes into lakes, you can actually get fish kills. So again, sulfur dioxide, nitrogen oxide turns into sulfuric acid and nitric acid, and then we have those weak acids come down and can kill forests, can kill fish, and can basically turn a sculpture into a big blob of stuff again. This is a little bit on acid rain. Whoa. Again, if you can't hear it, rewatch it.
Have a wide-ranging effect on the natural world. Rivers like this one in the Peak District can be devastated by contamination. Chris Curtis of University College London has been monitoring pollution and its effects on the countryside.
I'm just going to test the pH of this drinking water. This is good old London tap water. It's a comparison with acid river water sample. And as you can see, when I put the probe in the tap water, the pH goes up to about 7, which is circumneutral. So that's neutral tap water.
Lower numbers are acidic, higher numbers are basic.
The pH value goes down to about 5.2.
Which means it's acidic.
That's the difference of 2 pH units, but because pH is a logarithmic scale, that actually means it's not 10 times, it's 100 times more acid in the stream than it is in the tap water.
That's a problem.
So we're trying to collect the insects and other invertebrate animals that live under the rocks and in the gravel to see which species are present and see whether there are any acid-sensitive species present, which might indicate that this system is recovering from acidification. And what we can see is that there's actually not very much here. That might seem like a bad thing, but it just tells us a lot about the stream, and it tells us that the water quality isn't very good. In other words, it's very acid. If we went to a very healthy lowland stream with a high pH, we might expect to find a very diverse community of invertebrates living in the sediments and under the rocks in the stream. With the invertebrate thing that tells us that they could have been killed by acid episodes in the stream.
Rob Mills from Bangor University uses a different technique to test acidity in the environment. He is trying to assess the impact of acid rain by isolating small plots of land away from the influence of people and cars. In this first section of test plots, the soil is open to the elements as normal.
You can see they have a grid system so they can measure in individual areas.
But in the second block, a plastic cover shields the plants when it rains. Instead of rainwater, these sheltered plants receive the same quantity of distilled water. However, not all the moisture in the soil comes from rainfall. Some of it comes from the dense fog that regularly covers this area. This water can also be tested using an ingenious collection.
Okay, what this is we call it the cloud collector. Essentially what it does is it collects clouds. So as the clouds move across the hillside, they come across this fishing line wire, and small droplets from the cloud condense on here, run down into the funnel, and we collect it at the bottom. And this is another way of us getting an idea on how much acid material is coming into the system. We can have a quick look at this. And what we can find in here is that this will be full of a range of particles, and these particles are what the water droplets condense around. So this could be particles of dust from car, vehicle emissions, from fossil fuel power plant emissions, and each one of these tiny little specks of black dust could represent a single droplet. And of course this material then eventually enters the ecosystem, and the consequences of which we're trying to find out.
Another of Rob's tests assesses the effects of global warming. He covers some plots at night in order to raise their temperature. Over several years, Rob wants to see how the effect of temperature alone affects the plant's growth.
So this is long-term
Global
study.
warming is a product of a natural phenomenon. So naturally we have the greenhouse gases which exist in the atmosphere, which allow life on Earth to exist. But global warming is a function of what we term anthropogenic activity. That's all of human activity. And over the past few hundred years, we've been contributing a lot more of these greenhouse gases to the atmosphere.
Not right now, not as
Essentially
many.
what we're seeing is the climate is changing, not necessarily always getting warmer everywhere, but generally speaking, the climate is changing, and we can term that global warming or global climate change.
Okay. Again, if you couldn't hear that, this would be, this always in notes. Go back to the notes and watch them yourself. So remember I talked about the fact that we've got all of the surface area here, and as you break stuff down, the more it breaks into pieces, your surface area basically exponentially increases. So basically think about this. I've got a 6-sided cube, but I break that into 2, 4, 6, 8 pieces. Look at how many more sides, because each of these 8 pieces now has 6 sides. So, think about that. You've got 6 times 8, which is a lot more spaces. And then break that down again, and do you see what I'm saying? You've got more and more surface area. The more surface area you have exposed, the faster those chemical agents can break it down. So once it starts to crumble, it can go really fast to break into smaller and smaller pieces. And we also talked about the fact that water can pick up minerals as it seeps through the ground. It can pick up lime. And if it as it leaches down through here, if it finds an opening and it starts to drip, water has something called adhesion. It wants to stick, but eventually it will drip down. You can see little drips right here. And it leaves just a little teeny tiny bit of the minerals that it had collected as it, went through the ground and deposited. And you get stalactites in the cave. By the way, if you ever go into a cave and you see stalactites or stalagmites, please don't knock them over, because they took literally hundreds, if not thousands of years to form. So respect them. And how you remember a stalactite, by the way, versus a stalagmite. A stalactite has a T and a C, so it's tight to the ceiling. A stalagmite has a G and an M, and it's the mighty ground. So stalactites are on the ceiling, stalagmites are on the ground. And if they come together, you get a column. And that is all through chemical processes of chemical weathering, where you're actually removing it from here and depositing it here. And you can get beautiful structures of stalactites and stalagmites. So the ones hanging from the ceiling, stalactites. The ones growing from the ground, so as this drips down, it hits there and builds up. That's your stalagmite. And where you notice here, if you look right above the eye and tight, this is just about coming together to form a column. And this is in a pool. It's actually draining into a pool. And here are more stalagmites on the ground, mighty ground. And here is a column, almost is so close to being a perfect column, and then it starts to build up farther and farther. And you can see these, because then it starts to fill in, because as it comes in, it hangs out there and deposits a little more. So you can get these beautiful columns in caves as well. They're connected stalactites to stalagmites. Karst. We actually have karst in Minnesota, and basically you find it in southeastern Minnesota into Wisconsin and Iowa. And karst is a very water permeable limestone, and water is really good at dissolving it, so we get sinkholes. You can actually be driving along and you might see a field or somewhere else where all of a sudden, or maybe it's some trees, and all of a sudden there's a hole and everything has fallen down, and you see the tops of the trees because the roots are maybe 20, 30, 40 feet down in the ground. So seeping through this cave, as this top wears away more and more, we lose more and more structure above it, it can eventually collapse and you get a sinkhole. It happens in Florida as we remove water. So really quick, we can have water form stalactites or stalagmites. That's through a chemical process as it leaches the minerals out. Weathering with air can cause arches and other beautiful, so that's abrasion, right? And remember, this is a quick review. Another form of erosion that happens to water, and I'm re-including this because it is an erosion process that creates this. Rills are tiny grooves in the soil caused by trickling water. It wears it down. So these are rills. Remember, if they're big enough to step in, they go from rills to what? And I'm going to ask you that question. You're going to have to answer it. So that is the end of this set of notes on mechanical and chemical weathering. Again, we're going to do glaciers on a different day, and we're going to get to soil formation. Thank you for watching, and as always, if you've got questions, Zoom or email. Have a good day.